So this is sheet 6. This is like the bonus sheet. This contains much harder questions, and I'll just go through them. I'll speed run them as fast as I can, just to give you some kind of idea. Just to show you some more advanced techniques. Don't worry if you don't understand all of this. The main goal really here is tends to mull. That's where we're going. The product of the limits is the limit of the products. And as I say, I know a very short proof. I know a 2-line proof of this using filters, but we're going to see a much longer proof that does everything from first principles. So first of all, we're going to learn about multiplication by constants. So here's a sort of a warm-up question. Can we prove that if an tends to t, then 37an tends to 37 times t? So how are we going to do that? We're going to, I guess the idea is we want to make, so intros epsilon h and h epsilon. So now how are we going to make sure that 37an minus 37t is less than epsilon? We're going to make sure that an minus t is less than epsilon over 37, right? So we specialise h, epsilon over 37, and then we've got to prove that if epsilon is positive, epsilon over 37 is positive. So by norm num should do that. By Linarith should do that, sorry. And then we have our bound. So we don't even need to specialise. We can obtain xhx can be this, and then we use x, and then intros nhn. So now, and then we feed that straight back into hx, right? So specialise xnhn. And now, that has not gone well. Let's try specialising hxnhn. There we go, that's gone better. So now, what does that goal say? So you see the goal, we now know that an minus t is less than epsilon over 37. We want the 37an minus 37t is less than epsilon. And you would imagine that, if you were doing you were giving a lecture about this, you'll just say, now this is obvious, but Lean doesn't have a tactic that's going to deal with those absolute values. So, I mean, one could do it by hand. I guess one could do it like, I suppose this wouldn't be so difficult. I'm going to do it step by step. So we've got 37an minus 37t, and I want to write that as 37 times an minus t, so that'll be called mul sub, I guess. Did that work? Yes. And now we've got absolute value of a product, so that'll be called abs mul or something, or mul abs. Yes, it's abs mul. And now we've got this absolute value of 37, so that would be abs of non-neg, I think that's called. Abs of non-neg. There. And now we're in good shape, right? Because both of these goals should be solvable by Linarith. Does Linarith do that one? Yes, and Linarith does that one, so I can put a semicolon here. And that should do it. Yes, that did do it. And I've managed to Lean's in a funny state. Let me restart. Let me reload window. There should be a red line under that. There's no red line. There's my red line. Okay. So that's done that one, and that's sort of warm up for this one, which says that if what does it say? It says if an tends to t, then c times an tends to c times t. But the proofs are sort of slightly different depending on whether c is positive or negative or 0. So this is the positive one, and of course the proof's very close to this. So why don't I just sort of copy it here? And now let's see what we have to change. So instead of epsilon over 37, we need epsilon over c, right? And now, of course, Linareth won't solve this. We know that c is positive and epsilon's positive. We need that epsilon over c is positive, but that's a non-linear question, so I suspect, though, that it'll be in the library, so let's try library search. It'll be called divpos or something. There we go. Divpos there. So that's done that one, and now use x, yada, yada, yada. And now we don't want abs of non-neg now. We know that c is positive, so we probably want abs of pos hc or something there. And again, we have the problem that, do you see Linareth wasn't working? There was a red line under it. And again, this just looks like some standard fact. Again, the fact that c is positive means that we can mean that these two. So this will be in the library as well. In fact, it's going to be. Oh, there we go. It's this. It's LT div if primed. LT div if primed says that a is less than b over c if and only if c times a is less than b. The fact that it says LT div prime might make you wonder what LT div without the prime. What's it without the primed? It's the same thing but in sort of a slightly different order or something. But anyway, that's the joys of library search for you. So there's the proof that if an tends to t, then c times an tends to c times c when c is positive. And the next statement is that the same thing is true when c is negative. So let's try the same proof again. But here, of course, we don't want to divide by c. We probably want to divide by negative c. So why don't we do this? Have hc primed 0 is less than negative c. Whatever that's called. Oh, what have I done? What have I done? Oh, I've gone down there. Colon equals by library. I mean, I guess Linareth would prove this, but there we go. So you see, we're going to be using, so in half of this proof we're still going to be using c, because we've still got c times a and c times c, but in the other half of this proof we're going to be using negative c, because that's the thing that's positive. So now I want to divide by negative c. I want to divide by negative c. Lean red / less than as the beginning of a comment. And now this will be div pos hc primed. Now all this is still the same, but now I've got to, where am I in the rewrite? You see now I've got this absolute value of c, and the absolute value of c, now I need to use that c is negative, so this is abs of neg hc there. And now we're still using exactly the same. This is just, I'm just going to need that this needs to be hc prime, doesn't it? And there we go. As the good error, the best possible error tactic fail. There's no goals to be solved. So that's done. The limit of c times a is c times t. In the cases where c is positive and negative, and you can see the proofs are very similar, but they're somehow also very slightly different. Somehow, and this means that they need to be done separately, or at least I don't really know of a way of unifying them. So now here's the general case. We want to prove that c times an tends to c times t if an tends to t, and we want to split that up. So what's that called? LT trichotomy. I think LT tricot. Oh yes, there it is. LT trichotomy says that if a and b are in some totally ordered thing, then either a is less than b, or a is equal to b, or b is less than a. So when I do LT trichotomy 0c there, and I need to do a case split on this. So instead of have and then cases, I can do that with obtain. So obtain 8c or 8c or 8c. And now I've got three goals. So this is the goal with c positive. This is the goal with c is 0. This is the goal with c negative. So the c equals 0 case, I shouldn't even put 8c in. I should put, if I put ref, I'll do the refle trick. and then that middle case there doesn't have any C's in at all, it just has 0. And now the first and the last thing we've proved already, right? So library search should work. There. It does that. The middle case let's leave for a minute, and the bottom case I could just copy. It's going to be that, but neg instead of pos or something. Tends to neg const mul, hopefully. I've forgotten a comma. There we go, that looks okay. But we still haven't finished this level because we've got to do this degenerate case. You see, when C is 0, the proofs don't work, right? Because I've divided by C. So this is a degenerate case. So I sort of run the simplifier on it to get rid of the... You see, we had sort of various 0 times things. 0 times n and 0 times t. So the simplifier changes them all to zeros. And now this is, and now we can do this as well with library search, right? Because we proved that a constant function tended to a grade, tends to const 0. Actually, let me not do that yet, because if I'm doing simp and then exact, that probably means I can use simper. Simper using, does this work? Yes, it does. Great. So there's a there's the proof of that. So basically, we're using results we've used before. So there were there's no epsilons in that proof. We were just using things that we had already. So now what's happening now? Tends to mul const. Oh, this is just... I see. So we're saying that C times AN tends to C times T. Now we're also saying that AN times C tends to T times C. So this is, in fact, this is essentially, this is already tends to const mul. I mean, I could just sort of convert if I did. Yeah, I mean, I'll show you convert, but I bet we can do this with simper again. If we do convert this, tends convert. What does const mul need? Those are squiggly brackets, so we don't need to input them. It needs C and H, so let's put C and H in. And then you see, yeah, it's gone slightly too far. I mean, I see. Well, I mean, maybe I should persevere with this. Let's try using 2, using 1. There we go. So this is the proof using convert. We've got to prove that this function equals this function, and yeah, that somehow that would be x'd. Oh, I could probably do it with simp mul com or something. Yeah, I think if I do simp, yeah, simp won't solve it. Mul com is not a simp lemma. The idea with simp lemmas is that the left-hand side is supposed to be more complicated than you simplify the left-hand side to the right-hand side. So mul com doesn't feel like a good simp lemma because both sides are sort of equal complexity. Okay, so that means I can probably do simper mul com using that, and then let's get rid of that. Does that work? Yes, it does. So there's that proof, one line proof. In fact, because it's one tactic, we can just do. We don't even need begin end. We can just do it with by. So there you go. There's tends to mul const. And here's tends to neg prime. So what's going on here? We've already proved tends to neg. So if AN tends to T, then minus AN tends to minus T. But we're just observing that you can use, if we know tends to const mul, we can apply C as -1, you see. So if you use C as -1, then you get -1 times AN tends to -1 times T. Is them... Wait a minute. I'm assuming... I suspect that the simplifier will know this. Let's let T be a real. -1 times T equals -T. Yeah, the simplifier knows that. There's no errors. If the simplifier didn't know that, then there'd be a red underline on the simp. And so that means that actually we could yeah, I could just do simper using this or something. That would... Yeah, simply using this. So here's an even shorter proof than the one I thought of when I was writing the sheet. Just out of interest, where did this sheet come from? This was something I was doing with the first years last term. and I haven't really looked at it since. I just thought I'd sort of copy it and give it to you lot. So so it might even need some tidying up. So tends to sub. What does this say? We've got sequences A and B, and we know that AN minus BN tends to T, and BN tends to U, then AN tends to T plus U. So right, so that's tends. You see, we're not going to need epsilons for this either, are we? Because this just says if H1 and H2 are two sequences tending to limits, and then we could add them up, right? Because we know tends to add already, right? So this is going to be, it's going to be simpler using tends to add. If we're lucky, H1, H2, we are lucky. So there you go. And now this one tends to sublim. Oh, this one should be an if and only if, because it only has one hypothesis. Yeah, this would be better. This would be better as an if and only if. AN tends to T if and only if AN minus T tends to 0. We're going to need the other implication in tends to mul. So let me put a colon there. Let's call it tends to sublim if. I think that would be a better name. Tends to AT if and only if. There we go. I think that's probably the correct thing to prove. But I'm going to have to split it, I think. And now let's see if I can come up with one-line proofs of both of these. So what's going on here? Oh no, we can't. I mean, because we need to intro H. So now we know that AN tends to T, and we want to know that AN minus T tends to 0. So it's going to be simpler using what? So, we know that AN tends to T, and we know that T, the constant function T, also tends to T. And so, okay, yeah. Let me do, I'm a bit nervous, let me do convert. Convert tends to add, and then H is the first thing, and then we need tends to const T. How does that work? Oh, tends to, I'm a fool. Oh, it tends to sub. Let's see how that goes. This is great. So convert, and simp will do this. Great. So that means we can probably do simper using this. Did that work? Yes, that worked. So that can go there. And then it'll be, I guess the other way we'll use tends to add. So what do we know here? We know that, so intro H again. We know that AN minus T tends to 0, and we know that T tends to T, and so now we add those up. So simper using tends to, it's just going to be exactly this, but with add instead of sub, isn't it? Tends to add this. Did this work? Yes, that worked because I've got no errors. Lovely. So you see we haven't used any epsilons for a long time. But this one we're going to need an epsilon. So this is some of these, this is going to be harder. Not harder, we're going to have to go back to epsilons again. We can't get this stuff for free. You see tends to add and tends to const. So they're very useful things to have in the library because you know, in your API, because we're just getting other things directly very, very quickly from them. So what's going on here, if AN and BN both, so we're trying to prove that AN, the limit of the product is the product of the limits, and this is a special case, but I know quite a nice proof that goes via this special case. So let's do the special case is much easier to prove. So AN tends to 0 and BN tends to 0. So here's the idea, proof idea. Eventually, you know, AN will be absolute value of AN will be less than epsilon, and the absolute value of BN will be less than 1, right? That's the proof strategy, and hence, you know, absolute value of product will be less than epsilon. That's the you see, it's much simpler when things tend to 0. So that's the idea. Okay, so we need to specialize. Well, I guess it's we could obtain, can't we? Obtain x and h. Let's get a bound for a. We need an epsilon. So intros epsilon and h epsilon. And now this is going to be HA epsilon H epsilon there. So x is now the bound such that for everything bigger than x, an minus 0 is less, I mean, that should say an is less than epsilon, but the simplifier will catch it in the end. And then obtain YHY is going to be HB. Now I want 1, and now I need to prove that 1 is bigger than 0. I think that's called 0 LT1, right? Yeah, there we go. So now I've got the bounds x and y, and then the bound we're going to use the max of x and y there. And so now, if we're bigger than the max of x and y, then a will be less than epsilon and b will be less than 1, and so it should be easy. And now, so specialize. We need to specialize hx. Oh, we need the n. So intros n hn, and then specialize x n something. So we know that max xy is less than or equal to n, and we want that x is less than or equal to n. Well, library search do that one for me. I don't really want to. Yeah, we're lucky, so we don't have to start launching into Linarith. We can just. That's already in the library, so there. And then the other one we want HYN, and this will be LE of max, LE right. What does these say? Yeah, see max. Yeah, okay. So these are sort of they're sort of exactly the function that we needed to fill in the hole. So now we know that an is less than epsilon and bn is less than 1. Let's tidy everything up. An is less than epsilon and bn is less than 1, and we want an times bn is less than epsilon. And so that will be called. I see. So we could rewrite, what was it called? I think it was called abs mull. Abs mull. There. Right, and so now we're going to need. This is mildly annoying, isn't it? Because we need to know that the a's will be non-negative or something. See, I was thinking about using the non-linear arithmetic. I mean, it's unlikely. Is this going to be in the library? No, it's taking too long. So I'll tell you what we could do. I mean, I guess we could. Let me just do some experiments. What mull LT mull? Have we got one of those? What does mull LT mull say? We have got a mull LT mull. We got, oh golly, we've got 4 of them. Oh, I see. They're all sort of slightly different. They're all slightly different. This is the one we want, isn't it? This is mull LT mull. There, so HXHY or something. Yeah, exactly. So we could put some underscores in there. We could convert this or something. Can you do that? Is that even a thing? Oh, that is a thing. Great. And so now we've just got to prove, and that this will be in the library as well. Norms are non-negative. There we go. Yeah. Oh, does this work? Oh, it does. So then I can do this. and that should be done. Yes, great. So there we go. If an tends to 0 and bn tends to 0, then the product tends to 0. And I wonder if I can get, can I abs mul? See if I can be really cocky and get rid of that line. Yeah, there you go, that works too. Great. Did it? Yes. In fact, you could even get rid of the specialized lines by sticking them in there, couldn't you? Let's leave it. It's short enough. It'll do. Okay, boss level. We've got to prove that the limit of the product is the product of the limit. So here's the proof. Here's the proof I want to go for. So it suffices to prove an times bn minus an bn minus t times u tends to 0, and then you rewrite as an. I mean, the trick is you use the thing before, so it's an minus t, because an tends to t, times bn minus u, and then plus some junk. So what do I have to add? And there's a way of sort of sorting out all the junk. So this is an bn. Now we've got plus tu, so we need a minus 2tu to fix those. And we've also got the cross term, so I need plus tbn plus uan. We need that to tend to 0. And now there's a way of sorting this stuff out. This is uan minus I'm going to put one of the tu's with this. So this is kind of u times an. This is an times u minus t times u. So it's an minus t times u. There. That's one of the tu's. And then this one is bn, so t times bn minus u. And that's got rid of that one. That's a plus, I think, there. So that's the idea. And so I've written it as the product of it's the sum of 3 terms. And an minus t times bn minus u tends to 0, because we just proved that. And t times bn minus u tends to 0, because bn minus u tends to 0, and then we're multiplying by a constant. And similarly, an minus t tends to 0. So all of these things tend to 0, and so their sum will tend to 0. So that's the proof we want. And so we want to use that if thing there. This tends to, so there was epsilons here. This is going to be another epsilon free proof. Rewrite this. And so now we want to change a and bn minus t times u. So have h for all n a and bn minus t times u. That thing there. Equals this thing here, equals what? An, let's write it properly, an minus t times bn minus u, and then we add t times bn minus u, and then we add an minus t times u. There, that's my claim, and let's see if I got it right. Intro n ring should solve that claim, and it does, yes. So that should really, I have 2 goals at this point, so that should really go like this. There, and so now what? So now I'm hoping that we can do, can we do simp h or something? Yes, and that is, you see, now we've got this, now we've got this term here, and this term here. So we've got a sum of 3 terms, and they all tend to 0. So we want to use tends to add, and the conclusion of tends to add is that something tends to t plus u. But we've got something tending to 0, so let's just do a little hack. Let's do rewrite, show that the real number r equals 0 plus 0 by simp. there. So now I've got that something add something tends to 0 plus 0, so now I can apply tends to add. There, now you see we've got two goals. One says that the sum of the two things tends to 0. Oh, do you know what? We should just do this, shouldn't we? Let's get all three goals immediately. Apply tends to add. Yeah, great, that's worked. So the first goal is something complicated still, so that's also tends to add. Add something, and then something. We're refining, really, aren't we? What we're doing is we're refining the goal. And so now, hopefully, so now we've got three goals, and one of them says that, yeah, so this is in good. We never use, this thing here, we can rewrite it everywhere, in fact, because I don't think we ever use the fact that an tends to t anymore. We just need that an minus t tends to 0. Okay, great. So I'm just thinking, there we go, suffices this, rewrite as this, there. And now we have three goals, and the first goal is going to be, it's going to be exact. This thing here, tends to 0, mul tends to 0. There, and then HAHB presumably. Did that work? Yes. There, and now two goals left. And the first one is, actually library search will solve these now, won't they? Because we've proved them. Oh, what? Really? Why won't I might have made a mistake. And will library search solve? I'm quite surprised that didn't work. Oh, I know why it doesn't work. Because bn minus u tends to 0, so so t times bn minus u tends to t times 0. So maybe that second one there should be a t times 0. There we go, now library search. Now library search works. Excellent. And similarly, this last one should be 0 times u. There. There we go. Excellent. One tends to mul's constant, one tends to constant mul. So there you go. And there's tends to mul, and we've got, what have we got left? Oh, isn't that funny? All the time you sort of talk about the limit of a sequence, and you prove, right, here's observation. You learn about limits of sequences, and essentially the first thing you prove is that the limit of a sequence is unique. But we never use that in any of those proofs. You know, we said if an tends to L and bn tends, we never actually used the fact that that things couldn't actually tend to other things. So this is just I thought, for completeness, I thought we should prove tends to unique. And I guess, so what's the proof of this? The proof of this is, I know what it is. If S is not equal to T, then the distance between them is epsilon, and then you use the epsilon. It's another epsilon over 2 proof. You go sufficiently far away, A is within AN within epsilon over 2 of S and within epsilon over 2 of T, and that's a contradiction. So by contradiction, by contra whatever H. So H says that S is not equal to T, and we want false. And now, I guess we want epsilon. There's two ways of doing this now. We could either let epsilon somehow be the absolute value of S minus T, which we'll be able to prove is positive. Or we could do Woolog. You haven't seen Woolog yet, so let me show you Woolog. I'm not very good at Woolog. Woolog HST. Woolog H2. I claim that S is less than T. Does this? Yeah, this looks good. Okay. So I claim that Woolog S is less than T And Lean says to me, that's all well and good, but you've got to prove to me that for... Yeah, it's figured out... You don't normally think about this, do you? You just kind of say, well, log S is less than t, and that's by symmetry, right? But Lean has explicitly flagged... this has gone quite well, actually. Sometimes I can get really stuck with log. Lean has explicitly flagged that the extra goal we need to prove is that either S is less than t or t is less than S. Is that... Can we do that by libraries? That would be a nice thing to have in the library. That's great. There we go. Wonderful. That was a second goal, so that should probably go like that. And so now what? S is less than t. So now we don't need H anymore. The same that S isn't t, because we know that we have S is less than t. So now this should be easy now. So now let's set epsilon can be t minus S. There. I could use the let tactic, but I prefer to use the set tactic, because we're defining epsilon to be t minus S, but then the set tactic gives us a hypothesis, h epsilon, that says epsilon is t minus S. I wonder if we even need it, actually. You might actually be able to do this without introducing epsilon at all. Let me not do that. I mean, let's not. I'm already going pretty fast. Let's not try and golf in things anymore. So, have h epsilon is that epsilon is positive and 0 less than epsilon, and I don't know. That's bound to be in the library. There it is. And so you see, S is less than t, so t minus S is going to be positive. And now what? So now we feed epsilon over 2 into these. So obtain is the usual trick, right? Obtain xhx is hs, and that would be epsilon over 2, and this is by Linarith or something, hopefully. Yep. And obtain yhy for, let's do ht. There we go. And now what? So now we feed in, we need to make n, we just need one value of n that's going to mess us up. So we could use max of xy, right? So specialize hx, max xy, and then something, and the something, we need to prove that x is less than max xy. So let's put by library search, because I forgot, that's going to be, what's it called? LE max left, so there we go. And then hy max xy, and that's going to be called LE max right. There. So now we know that's, you see, so now we should have our contract. I mean, we know how to do these now. We rewrite what was it called, abs lt at hx and hy. I recorded the sheet 5 video just before this one, so and now hopefully Linarith will get the contradiction now. We won. So that's the end of that. So there we go. That's me. That's the kind of way I would sort of write Lean code in real life. Oh dear me, I don't know, there's spaces there. There. That's, yeah. I mean, I wasn't really sort of in teaching mode there. I was in, let's just plough through this incredibly complicated sheet because I didn't want the video to go on for too long. But there's group theory next time would be rather less crazy. So apologies for the sort of rather fancier tactics, but we're going to get back down to some simpler stuff next week.